What if one of the biggest ideas in all of physics was actually just a clever shortcut? We're about to dive into a thought experiment that takes that famous train problem from Einstein, but looks at it with a whole different set of rules. And it's going to make us question what our scientific models are really telling us. Okay, so it all kicks off with something you've probably seen before. A train, just blazing along at a huge chunk of the speed of light. We're talking 0.6 c. Yeah, this is the classic setup for special relativity. But here's the deal. For this explainer, we're just going to throw those rules right out the window. So here's the big twist. What happens if we just pretend relativity doesn't exist for a minute? The author of this whole thought experiment wants us to tackle this problem using only old-school classical mechanics, Newton's physics. And the real question is, what kind of answer do we get then?
All right, first up, a train in space. See, if we're going to analyze this classically, the author says we need to set up a totally new playing field. We need, like, a universal, perfectly still backdrop that everything else moves against.
And they've got a name for it, base space. Just picture it as this absolute, totally on-moving grid, a universal electromagnetic field where the train tracks are just sitting there, completely at rest. Now, this is a huge departure from relativity, right? Because relativity says there is no absolute at-rest frame. But in this model, base space is it. It's the one true stationary background.
Okay, Section 2, Light's Path, a classical view. So now that we have our base space all set up, let's zoom in and look at a simple beam of light inside that train. And remember, we're still only using classical Newtonian rules here.
First, let's do the easy one. The train is just sitting still. A photon gets fired from the ceiling, and it goes straight down to the floor. Easy. If we say the height of the train is, say, 1 unit, then the light travels a distance of 1 unit. Super simple, no tricks.
Okay, now for the fun part. Let's get that train moving. From the point of view of our totally stationary base space, think about what's happening. The train is moving sideways, at the same time the light is moving downwards. So the light's actual path through that base space isn't just straight down anymore. No way. It's now a diagonal. It basically forms the hypotenuse of a right-angled triangle.
So, naturally you're asking, how long is that diagonal? Well, bust out your old friend the Pythagorean theorem, and the author crunches the numbers. Even though the light looks like it's just traveling 1 unit down inside the train, its real path through the base space is actually longer. It comes out to 1.166 units. And trust me, this number is the key to everything.
Section 3, the apparent speed of light. Okay, this is where it really gets wild, because if the light is physically traveling a longer distance, what does that mean for someone inside the train? What do they actually see?
The author gives a pretty cool analogy for this. Think about a ferry trying to cross a fast-flowing river. If you want to go straight across, you can't just point straight across, right? You have to aim a little bit upstream to fight the current. Well, it's the same idea here. The light has to travel that diagonal path through the base space, so that for the passenger, it looks like it's just going straight down.
And this brings us right to the heart of the whole argument. The passenger, they only see the light go down 1 unit. That's all they experience. But we know it actually traveled that longer diagonal path, the 1.166 units. So if it traveled a longer distance in that time, from the passenger's perspective, its speed has to seem slower. The math works out that this apparent speed is just 0.857 c. Only about 86% of the actual speed of light.
So, you see where this is going. Here's the bombshell conclusion of this whole model. For someone on that train, the speed of light is not a constant. It actually looks like it slows down. And that flies directly in the face of Einstein's second postulate, which is the bedrock idea that the speed of light is the same for everyone, no matter how fast you're going. All right, moving on to Section 4, a base reality. And, the author doesn't just leave it at the train. They take this core idea and blow it up into a much bigger model of reality itself.
Just to make sure we're all on the same page, the entire argument really boils down to this one distinction. You've got base space. That's the absolute, fixed, real reality. And then you have physical space. That's our moving point of view, like being inside the train. And all these weird effects, like light seeming to slow down, they only happen in our physical space.
To help us picture this, the author gives us a more abstract image. Imagine base space reality is this giant fundamental sphere, and our own moving realities, our physical spaces, are like flat planes that are just tangent to that sphere, just barely touching it. It's a way of trying to visualize this whole two-level idea of reality using geometry.
Okay, final section, the map versus the territory. So why bother with all this? Why go through this whole complicated thought experiment? Well, it's to get to the philosophical core of the argument, which is all about the difference between our scientific models and actual reality.
And the author sums it all up with a really famous saying: the map is not the territory. The idea is that our scientific theories, even something as powerful as special relativity, are basically just maps. And they're fantastic maps. They help us get around, predict things, but we should never, ever make the mistake of thinking the map is the actual territory, that the model is reality.
And this is where the author really starts to poke the bear, asking some really tough questions. Could special relativity, for all its genius, be a kind of mental short circuit? A brilliant map that's so good it actually makes us forget to look at the real world underneath? What if things like time dilation aren't actually properties of space-time? What if they're just side effects of us moving through some kind of real physical medium, this base space that we just gave up on looking for?
At the end of the day, this whole thought experiment isn't really about trying to prove Einstein wrong. It's more of a challenge to how we think about science, period. Are our scientific models a crystal clear window into what's real? Or are they more like a picture frame that actually limits what we can even see in the first place? It's a powerful reminder that even the very best maps we have might not be the territory after all.